Hello everyone. Looks like we have almost everybody. Everybody's registered is logged in here, so I think we're going to go ahead and get started with our webinar today. Once again, thank you for joining us for another of our LabChart Mastery series of webinars. Today we're going to cover calibration and setup of your MPVS Ultra unit for using with PV Loop recordings. My name is David Ream. I'm the Technical Support Engineer for AD Instruments North America. And before we get going here, I want to talk more about the GoToMeeting interface, kind of some of the particulars that we're seeing here, and just so that you guys know how to ask questions and interact with me. So as you probably noticed, all audio from attendees will be muted during the presentation. This is to kind of keep any background noise down and also keep us on track so that we can cover all the material that we want to cover today. The primary ways that you can interact with me is via the GoToWebinar toolbar. So you see here on the left-hand side we have a screen capture of the Macintosh version. On the right-hand side we have a screen capture of the Windows version. So if you have any questions or comments during the presentation, go ahead and enter them in the questions window, and after I've covered everything we're going to cover today, I'll go ahead and discuss each question in the order that it was received. If you have any problems with audio, you can ask it through questions or just mention it, or through the chat window as well. Also, before we get going, I want to talk about kind of our upcoming training calendar. What we're seeing here is actual physical LabChart courses. So July 10th through the 11th, you can come see myself and Brandon Boucher here in Colorado Springs and attend our LabChart software training course levels 1 through 3. These are all chargeable courses, I believe. So definitely talk to your sales rep, talk about pricing if you want to come out and actually do a physical course. We're going to follow that up with another one, software training course level 1 through 3 on the 24th and 25th of July at our Boston, Massachusetts location. Also, we will be participating in Northeast Ohio Medical University's microsurgery and echocardiography workshops the 12th to 16th of August. That's in 2013 in Rootstown, Ohio. There will be a number of AD Instruments staff there to kind of discuss how, once we've learned the microsurgery techniques, we're going to cover how to use PowerLab and LabChart to bring that data into LabChart and actually analyze it. Also, here are the upcoming LabChart Mastery Series webinars. On the 9th of July, Brandon Boucher is going to cover using the datapad. And then I'll follow up on the 25th of July, talk about using the sampling feature in LabChart as well as the scheduler extension to kind of talk about automating LabChart and only recording the data we need over specific periods of times. If you have any questions about what's coming up or curious about further out what we have scheduled, I would recommend going to our website and going to the Events tab, and you can go there and kind of see our upcoming calendar both for North America as well as for our other offices across the globe. Also, a little bit of boilerplate here. These are quite often we get this question from customers. You know, how can I use my LabChart and the PowerLab? What can I connect it to? What are the limitations? You don't have to read all of this right here, but the take-home message is just that our products are not intended. They are not medical devices. They cannot be used to diagnose, treat, or monitor a subject. So that's the big take-home message from everything that's getting mentioned up here. Just they cannot be used for diagnosis or treatment or monitoring. Next, kind of keying into that same question, how can I connect things? How do I know that I'm safe to connect it to a human test subject? Any of our equipment, for instance our bioamps or some of our isolated stimulators that can connect to a human directly, will have the body protected symbol, the little man there in the square box. If it is allowed to be connected to have a direct electrical connection to the heart, it'll have the cardiac protected symbol, the heart with inside the box. Last but not least, quite often I get customers, well, how do I know what I'm reading in LabChart is actually what I'm getting into the front of the PowerLab? The way that we ensure this, we've actually been certified through this quality management system, ISO 9001. It's at some considerable expense, just to say that we manufacture, test, and service our software and instruments to a known good standard. We have proper quality measures in place so that you know what is actually going in the front of the Power Lab is accurately being reproduced in LabChart. So quite often if you have some sort of lab review talking about your experimental protocols, they'll ask for documentation for certification that the products you're going to be using have been produced to a known good standard. We actually provide our certificate on our website for this quality management system. So, moving on to the meat of what we're going to talk about today. So first I'll give a general overview of the MPVS Ultra control software. We'll talk about pressure calibration. The pressure calibration steps are identical for small, large animal procedures. And then we'll talk about small animal volume calibration procedures, large animal volume calibration procedures. There are some very large differences that we want to cover. Then we'll talk about saline calibration, how to talk about removing the conductance of the heart wall and actually getting good, accurate volume readings and not having any sort of influence from the tissue that's surrounding the ventricle. Then we'll also talk about the alpha calibration, the end-all of end-alls to compare what you're getting with your Millar catheter, your Millar and LabChart and the Power Lab. Compare it to, say, something like an echocardiogram to know that, okay, we're calibrated and we know we're even going against a known standard here, so we can take care of any variation at all. So on that note, I'm going to go ahead and clear out of my presentation and we'll move right into LabChart and the MPVS Ultra software. So on the left-hand side here, I have LabChart open and some data we've collected previously, and I'm going to kind of move back and forth between LabChart and our PV Loop module and also the Millar Instruments Ultra control interface. So on the right-hand side here, we have the MPVS Ultra interface. This will be the first thing that will come up, and we'll kind of talk about how to connect your catheter, what's kind of going on here. So I do actually have a catheter connected here. I have an SPR 839. It's a small animal catheter, 1.4 French, and you can actually select your catheter from this list that appears here. So say I'm not using the SPR 839, maybe I'm doing large animal work. I can go in here, and we notice this. We have this button here that says Catheter Configuration Locked. If I left-click this, it unlocks. I can mouse up and down here and find my specific catheter and select it. Then the MPVS Ultra software will change the interface to reflect what that catheter is capable of doing. I'm going to leave it set here for my SPR 839. I'm going to left-click again the catheter configuration unlock button right here, and it's relocked. Once again, to change your catheter type they're using with the MPVS Ultra, catheter configuration locked or unlocked, and then we can go in here and select and move on to our specific catheter. But I'm using an 839. I'm going to go back here and lock it. It's relocked, and the button actually turns amber. We also see here up in the right-hand corner that I have good power from my MPVS Ultra. I'm connected, and I've also connected a catheter. Later on, I'm going to use the software in simulation mode because I do not have a large animal catheter to kind of talk about its calibration procedures, and you'll kind of notice that this will, I believe, turns red. Also, do I want to remove or add specific catheter models? If you know you're not going to use half of these catheter models, you can remove them from the list, so it'll make it a little bit easier to go through and select. I can also create a new catheter, enter things in, tell it what the spacing is, etc., etc. So as I said, I have an SPR 839 connected. Just kind of the general look out here, blood resistivity. It's not something we're going to worry about with a small animal catheter like the SPR 839. It's going to tell us, according to what catheter type we have selected here, is it single field? Is it dual field? Of course, we have a small animal one. It's dual field. We have our excitation electrodes and our sensing electrodes, only one field. Excitation current, is it low? Is it high? Depending on the catheter model. Alpha correction, we'll talk about that a little bit later. Volume range. the gain that we're using for this specific catheter. You can change this. I would stick with the default settings that Millar is providing here in the MPVS Ultra interface. However, if you find that you're going out of range or you're not have quality or a good enough resolution to actually see the changes you're looking for, you might want to change this. So that kind of covers our initial introduction to the catheter configuration page. Once we go on to the large animal, and I use the software in demonstration mode, I'll talk about how to change your fields according to how many electrodes you have on the catheter. And of course, we have a help menu, registration of the device that we're using, that you'll have to enter a code when you first connect your MPVS Ultra to the computer. Of course, you want to install the software first, then connect the device, and it'll request the code to actually unlock it and use it for large animal work. And we can also export this data to Millar's legacy software, PVAN. Next, we're going to move on to the catheter calibration tab. And this is where the meat of what you're going to be doing is both for small and large animal. So we're going to kind of move on here to the actual pressure calibration. Like I said, this is going to be exactly the same in either small animal or large animal. So Millar catheters can have 1 to 2 pressure domes on them. For my 839, I only have 1 pressure dome, and it's connected here to pressure 1 input. Right now, our balance is locked. And balance refers to actually zeroing the catheter. Every transducer is going to have some amount of offset. So we want to go ahead and take care of that before we do any 2-point calibrations to make sure that we're actually getting full range from our device. And of course, if I had pressure 2 connected, we would actively be seeing some recording here. It's way off scale because I don't have anything connected at all. And this whole region right here is going to take care of our pressure calibration. So right now we have it set to transducer. The MPVS Ultra can provide a variety of calibration signals out, but we'll talk about that in a second. We can also tell pressure 2 select what is it. Is it the secondary or the primary? It's going to be the secondary for in this instance, but we don't have anything connected. So how do I remove an offset in the catheter? I would go ahead and left-click Balance Unlock. It's unlocked now. It's green. We can go in here. We have it set to transducer. We're actively reading from our pressure transducer. And we can determine how much offset there is for the catheter. So if I just leave things as they are, you can see we have roughly about a 33 millimeter of mercury offset with this catheter. If I left-click Auto Zero, the MPVS Ultra software looks at the catheter, zeroes it for us. Like as I said before, if we have a second pressure transducer on the catheter and have it connected, we can also go here and auto zero for it as well. Once we've gone and auto zeroed and taken care of any offsets in the catheter's transducers, we can go here, left click, and lock the balance. Our next step is going to be calibration. And to do that, we're going to want to go here and either output 0, 25 millimeters of mercury, or 100 millimeters of mercury. And this is the MPVS Ultra control unit actually sending out a calibration signal out of the analog outputs and into LabChart. To use these, what we'll want to do, we would start recording, click them, let them record at a specific level for maybe about 5 seconds each, and then stop recording in LabChart. What you'll end up with is a data trace that looks something like this. And we can use this data trace to actually go ahead and do a 2-point calibration in LabChart. There's 2 ways you could do this. With our new PV Loop 2.0 software module, you can actually go and perform a pressure calibration here that gets you to units conversion. Or if you prefer to use it without the workflow mode that we currently have in PV Loop 2.0 that was introduced with it, you can go back to kind of what you did prior with PV Loop and actually go, let me make a selection out here in LabChart and go to units conversion and apply it here. I'm going to go ahead and actually cancel that, and we're going to use the PV Loop module. Prior to doing any of this, we want to tell PV Loop, are we doing a small or large animal protocol? It'll populate the list accordingly. We also want to tell it, okay, pressure channel is channel 1, volume channel is channel 2. It checks, and we can just go through the whole process here in the proper order. So we've recorded our calibration signals. I'm going to go ahead and apply those here. I'm just making a selection over our steps, entering them 25 millimeters of mercury, 100, corresponding to what we're getting whenever we press these buttons out from the Ultra. I check this box, apply, and now we're calibrated. And you can see here I'm going to drag out a small digital voltmeter. We are no longer reading in volts. We're reading in millimeters of mercury as I mouse through. This will be exactly the same regardless of whether we're doing small or large animal. If you had wanted to do this the old way, we can uncheck it, highlight our region where we've recorded our calibration steps, go to units conversion, select and use millimeters of mercury. We can also choose the decimal places here as well, apply to all new data, hit OK, and we get there the same. Just via a different route, we get the same results. So you can see here, as I mouse through them, with that applies to all old data, or if I record new data. I will have the units conversion over from volts to millimeters of mercury in LabChart. Do you have to use these pressure outputs? Do you want to trust them? Do you want to actually have a solid gauge reading, just that you know everything's going to be correct? You can also verify. You can. You don't necessarily have to use the calibration outputs. You can have a mercury manometer, a delta cal digital calibration unit, a column or a simple column of water if you want to, and perform the calibration yourself just by staying in the transducer mode and recording the different pressures here. If you want that, epitome of, okay, we know for sure, we're not relying on the Ultra unit to put out the proper calibration signals, you can do that as well. There's no right or wrong here. I'm going to go back in here, apply this. So we've done our pressure calibration. Since we're using a small animal catheter, I'm going to go ahead and talk about the small animal procedure first and how we can go and actually calibrate for volume. It's called the conductance calibration in the PV Loop workflow mode in PV Loop 2.0. However, just like with pressure, if we wanted to go ahead and apply this with an older version of PV Loop, say you're using chart 5, you can definitely go ahead and just do units conversion like I showed before with the pressure. You also see here, if I go back to catheter calibration, we have our volume section here. I can show it in conductance units, millisiemens, or in microliters. The key thing to remember about the unit that's being applied here, these are relative units. They have not been adjusted to take into account the parallel conductance of the heart wall. They have also not been had a Cuvette calibration applied, which we're going to talk about in a little bit. So do not use these values for your final analysis. You want to go through and provide and take care of all the corrections that we need to do prior to analysis to make sure we're getting good, accurate data from what we're recording here. We're taking care of all the variables that are there. So I'll actually put it over here into conductance just so that we know we're actually getting not a real volume unit. And the reason we kind of have this placeholder unit before we do a lot of corrections to it is just so that the calculations that PV Loop's going to do, or if you're using the PVAN software, just to make sure we don't have any negative numbers in there that can skew it and not work well with the equations. This just gives us those positive numbers so we don't have, as you can see down here, negative voltage values. So now that we're on the volume side of things, how do I do my initial kind of relative volume calibration? Right here, I'm reading from the transducer right now. I'm actively reading from my SPR 839. So we're kind of seeing a relative microsiemens unit. Just like with the pressure transducers, we have calibration outputs that we can put out. And just like, oops, sorry about that. Let me go ahead and go back here. Just like with our pressure calibration, we can send those out and actually record them in LabChart so that we get a selection similar to this. Of two known good voltage values that correspond to a specific millisiemens value or a microliter value. We can use a new workflow mode in LabChart PV Loop Module, as I mentioned before, or we can use the units conversion option as well. I'm going to use the new PV Loop workflow since we've already kind of covered how to do it the older way through the units conversion. So you would actively record. We would go through here, click our calibration outputs, record them into LabChart. Stop recording. Then we can go in here and select. Left click. That will be 1.14. Select here. And that will be 2.78. Apply the conductance calibration, and now you can see our data is no longer in volts, it's actually in millisiemens. Like I said, you can use microliters if you want to. Just keep in mind that is not a firm value. We would need to change that. It's not the final volume calibration. You're going to have to apply some corrections to that. So we've gone through, we have our relative volume unit. Now that we have a relative volume unit, we can go through and start sampling. Everything's kind of set up for our catheter. We can go ahead and gather our data, do some sort of calibrate. We can go through and just do whatever work we're doing, IVC, et cetera, et cetera. And then once we've gone ahead and finished our experiment, we want to perform a saline calibration and a Cuvette calibration. These are designed to give a known good volume and also to take care of any parallel conductance of the heart wall. In small animals, it's important to do the saline calibration before the Cuvette calibration as far as data goes. With the Cuvette calibration, you have to remove the animal's blood volume and actually put them in a Cuvette that I'm going to show here in a second. So obviously it's tough to inject saline into the animal after we removed all of its blood volume. So the first thing we're going to do is we're going to do a saline calibration. To show you what a good saline calibration looks like, we'll go ahead and go to one in this data file. So here's one that's been applied. And basically what we're doing here, we're injecting a known volume and a known concentration of saline into the vena cava, or somewhere in the venous return to the heart, and we're seeing what that conductance, what that change in conductance of the volume does. And from its behavior and how it compares to kind of the unity line of end-systolic and diastolic volume, we look for a parallel conductance volume that we can subtract from the volume values to remove any influence of the heart tissue from the actual volume calibration. This is definitely a bit of an art here. You probably will not get it right the first time. There's no real hard and fast, okay, this much volume, this concentration of saline. You're going to kind of play with the values and see what gives you the best results with your particular animal model. What you do want to see from a good saline calibration is minimal impact on the pressure channel. Let me see if I can move on to a... These are looking okay. Very minimal impact, as little as possible, because obviously we don't want to affect the pressure by affecting preload of the heart with too much volume. We're doing okay here. And also we want to see this kind of change here in the volume the volume channel. This kind of ramp up and increase in amplitude. Baseline shift and increase in amplitude. What will this look like in the PV loop view if we do a proper saline calibration? If I can get it to show. Something like this. A gradual volume increase, very little pressure change. None at all if possible. And this is what we'll know is a good saline calibration. Let me bring out the chart view again. How fast do I want to do this? Over about 7 seconds. We want to have at least 8 to 10 actual beats here in this region that we're going to select to actually apply it. And in a little bit here, I'm going to talk about how to take data from a good saline calibration like this and apply it to your actual recorded data. But first, we're going to kind of go on to the Cuvette calibration. The Cuvette calibration uses cuvettes sold by Millar and us, of course. That I will actually use. They're of a known volume. So basically, we drain blood from the test animal, actually use it, apply a little bit of heparin to it, or coat the wells here in the actual cuvette with heparin, and just kind of keep things from clotting. Fill those wells, take our catheter, and dip it in each well and record our results into LabChart. Once you record those results, we can do a cuvette calibration and actually apply any sort of correction factor to the equation being used to calculate the volume. Like I said, with small animals, we're going to want to do this, and actually you would only use a volume calibration cuvette with small animals. There's a different calibration method with large animals. You would only want to use this with small animals, and of course you only use this after doing a saline calibration and then draining the blood volume. Do we want to keep this warm? Yes. Put it in a water bath, 37 degrees Celsius, to keep things as close to the actual environment in vivo as possible. So once we go through here and dip our calibration, or dip our catheter through, what is that going to look like? So let me go out to our region where we did that. And you can see here, we've actually marked it with comments. Well 1, well 2, well 3, well 4, well 5. We want to use about that amount of wells. We don't want to just do 2 wells and then just apply that. Now you'll notice there is a Cuvette calibration window. That will actually have to go through whenever we click on this Cuvette calibration option, it will actually appear. Or we can access it via the PV Loop drop-down menu and go to Cuvette calibration. Your specific well will have known volumes associated with each well. You would have to enter them in here manually. So 6.19 for the specific catheter in the well you would use for it. 11 microliters, 17.18, 24.72, and 33.67. So we've gone through here, we've entered our known volumes. Noel, how do we go ahead and apply the actual conductance to these? I would go ahead and select here in our first column. Go down here in the chart view, select a region where things are nice and stable, set from selection. And you see we've added it for the 11 microliter well. And then it moves down for our next calibration. Go to well 3, make a selection, set from selection, and just kind of march through our Cuvette calibration. Can I do more than one and include it? Yes, you can. We have a few here. Just to kind of get better results. And you can see LabChart's going through and actually averaging here. You can watch our actual calibration equation change here. And once we've gone through all of our Cuvette calibrations, they correspond to known values, we can actually apply this. So we want to have a nice linear fit here and have a nice scatter of data points here to actually apply the Cuvette calibration. I hit apply, we go over to microliters, and it's applied to LabChart. So now that we've gone and done our Cuvette calibration for our small animal procedure, we're going to go ahead and do the saline calibration. And actually, before I think we get too far into that, I'm going to talk about the actual row Cuvette calibration with large animal procedure. And that will take place almost entirely within the MPVS software. So I'm going to go ahead and close the MPVS software, and we are going to use it in demonstration mode. And you can see here, no catheter detected, but we are using it in demonstration mode. So how do things change with a large animal? I'm going to go ahead and unlock the catheter. We're going to choose we'll use the 5790 should be there we go. We have a multiple segment catheter, large animal here, and this is how it changes things. You can see here we've gone to a dual field. It's telling us about the dual field here. Excitation current has gone to high. Nothing really has changed in here, except we have different, we can use conductance if we want to, or we can use milliliters if we want to, just accounting that, okay, we're using a catheter that's going to read a larger blood volume. Pressure calibration is the same. Initial volume calibration is the same. Say, for instance, our particular animal is not going to use all of these segments. Can I change them? Yes, you can. If I unlock the catheter configuration, I can activate this one. Bear with me here. And I can march down and turn everything off if I want to here. And keep marching my catheter down and controlling how many segments I'm actually reading from and where my actual excitation electrodes are located. And that's how you would go through here. So say I wanted to march down again, inactivate, secondary proximal, and then I can go ahead and move my primary proximal down and just keep controlling the width of our sensing region and also the width of our field that we're generating inside the left ventricle. So this is the way we can add more segments or decrease. Of course, we can go in here and change with the catheter configuration lock, just like we can in small animal, change the volume range, lock our catheter, and then we're actually reading the region we want to off the catheter for volume. As I said, the kind of general initial kind of placeholder calibrations are good. Pressure is exactly the same. Same thing with volume. We would go ahead and send out the calibration signals from the MPVS unit to LabChart to record our 2 steps that we're going to have. Now when it comes to actual kind of a volume calibration correction, you would actually use what is called the row cuvette. This is much different from what we're going to use, what we'd use in small animal, and it actually takes place entirely inside the MPVS software. So what is the row cuvette? What does it look like for large animal? This is the row cuvette. It plugs into the MPVS Ultra, and we actually have a small well in it where we would add some heparinized blood from the animal maybe initially, actually before we even start recording. Go ahead and add some in there and actually perform our row cuvette calibration. Of course, we want to warm this as well, water bath, etc., just to make sure things are exactly as they would be in the body. How do I set up the MPVS software for my row cuvette? We would go in here and create a new cuvette because this will be blank initially. We can name it whatever we would like. What's our cuvette model? And enter the K factor for that cuvette. Where do I find the K factor? Each cuvette here on its cord will have its specific K factor that Millar has measured for it. We go ahead, plug it in, set up our cuvette, put our heparinized blood in it, make sure everything's warm as it should be. We hit measure, and we receive our measurement snapshot, which would be the resistivity of the blood. I don't have a row cuvette connected right now, but we would have probably much better parameters if we actually have one connected there. I go to catheter configuration. Here is our row cuvette calibration values that are going to be taken care of by the MPVS Ultra unit before the data even gets to LabChart. And you'll notice in the PV Loop workflow mode, if I switch to large animal, I actually lose my cuvette calibration. I simply have my initial placeholder volume calibration sampling, and then we can do saline and alpha calibration. So depending on what animal model we're using is kind of how we actually do some of our volume corrections. So small animal, we actually use the cuvette, and that's going to be specific to your catheter model. Large animal, we're going to use the row cuvette calibration to actually enter a correction factor into the calculation that the MPVS Ultra system itself is doing. And you wouldn't need to do anything with LabChart. Okay. So that takes us through how to do the volume calibration with the MPVS software interface, as well as with the in LabChart. Next thing I'm going to move on to is the actual saline calibration. We talked about before saline calibration, what things should look like. Let me go ahead and move to our saline calibration area. I'm going to make a selection here. I'm going to analyze with PV Loop, and that gives us our region that we're going to use for the saline calibration. So actually quite nice here. We have our nice volume increase at ISO pressure going across. So here's where we're going to determine, okay, this is responsible for the heart, from the heart wall, and this is actual blood volume applying here. I can do multiples of these. So for instance, I'm going to go to my first saline calibration. I'm going to make a selection right where we start increasing. PV Loop, analyze selection, and I'll add that to my parallel conductance, my actual correction factor that LabChart's figuring out here. We have a lot of loops here. It's really nice. It's a good saline calibration. The volume channel is doing what it's supposed to. We have a nice dispersal of the data points here to get a nice good linear fit. We have a lot of data points, 14. And right where it crosses this unity line of when end diastolic and end systolic are equal, that's going to be our correction point to actually remove that parallel conductance that the heart wall is responsible for. Do I want to do one? You can, but like I said, we can go through and do more. I'm going to go to my second saline calibration. Once again, analyze, selection. Have a nice good dispersal, a few less points, but we're good. Hit add. And then we'll go to my last one. Make a selection here. Analyze the selection with PV Loop. Got a nice dispersal here, a good amount of loops, and add. Now I can choose whatever correction factor I want here, so I would probably go ahead and just pick the one in the middle. Looks like that first one right here is right in the middle. We can apply our parallel conductance. Because I really wasn't collecting this data actively, and it was actually recorded quite a while ago using relative volume units instead of microsiemens. My volume calibration may not be ideal, but ideally when we actually apply the parallel conductance, we're going to go down to roughly 0 with our volume. Remove any sort of influence of the heart wall. And you'll see a much more physiological signal out in the baseline regions. So we're still reading a bit high just because, like I said, I'm doing this after the fact on some data that was recorded quite a while ago. So those are the kind of the basics of the volume calibration here. Next, we're going to talk about the alpha calibration. And this is where we can actually take our echo data and say we figure out stroke volume from some sort of reference. Echo, some other method that you're going to find out to actually calculate a reference stroke volume. We look at our stroke volume for the Millar catheter. We can also use cardiac output if we'd like. And it gives us a correction factor against a known good standard to take care of any variation at all, any at all. You can either do this In the PV Loop software, you have to have 2.0 to do that, or the PV Loop module, I should say, in the LabChart software. Or we can go out here and apply it to our catheter, figure it out by hand, and apply our alpha correction factor. And that way, we wouldn't even need to do this step here in PV Loop. The MPVS Ultra unit and software is taking care of all of it. As I said, this is to take out any variation we're comparing to a known good, such as echocardiogram, etc. So that kind of takes us to the end of everything I wanted to cover today. So it looks like we may have a few questions.